Now that we've discussed angular kinematics and angular dynamics, it stands to reason that there would be angular momentum, which is the tendency of an object to keep spinning or turning, rotating or revolving. It's useful to recall that linear momentum is mass times velocity, that is a vector dependent on the velocity. Angular momentum is given the symbol capital L and is also a vector dependent on angular velocity. If we think about this as momentum equal to the inertia of the object, as we saw previously, times the motion of the object, then you can see that the analogy is pretty straightforward, that in terms of angular momentum, we're going to use the angular inertia, which we've seen as moment of inertia, times our angular velocity. I took pains to write it all out in words, but of course you can write that very easily as L as a vector is equal to I times omega as a vector. And the angular momentum would be dependent on the direction of spin of the angular velocity. This would be measured in kilograms times meters squared divided by seconds as units. But what's key in angular momentum is that total angular momentum of a closed system is conserved for a closed system. So we have the same type of rule that we saw in linear momentum, and so L is equal to L prime. So in this case, I times omega is equal to I times omega prime. I show you this because this is actually something that you're fairly familiar with. If we carry through the variables for omega and I as we saw before, the moment of inertia of an object, let's just assume is a hoop or a point mass for now. The fractions, of course, would cancel out anyway, so it doesn't really matter. Let's say mr squared times omega is equal to mr squared times omega prime. Omega we can put in terms of our linear velocities. So we have mr squared times v over r equal to mr squared times v prime over r, keeping in mind that this r, r1, and r2 don't necessarily have to be the same radius, right? But they are the same on the right-hand side versus the left-hand side. So this r cancels out the squared on both sides, and this reduces to m times r1 times v equals m times r2 times v prime. Assuming that the mass stays the same, we can cancel this mass. Now, it might be the case that the mass could change, and we can see the relationship further. But if we're talking about someone like a gymnast or a dancer, when they spin, they start with their hands out, and then they change their motion by moving their hands in, thereby reducing the radius from what it was, r here, to an r here that's much less, right? So this would be r1 and this would be r2. And so by angular momentum, we see that if I reduce my radius, then my velocity increases. And so we get the exact effect that I spoke of, is that if I pull my hands in while I'm spinning, I spin faster. So by changing my moment of inertia, my distribution of particles, I change my rotational rate. And so angular momentum is very useful in analyzing that type of motion, especially when a system is remaining constant in terms of mass.